All right, so now we will look at, now that we know that changing electric fields give us magnetic fields, and therefore, well, let's maybe state on the side what we have so far. So changing electric fields give us magnetic fields, to be more precise, changing magnetic fields. But anyways, if there's a change of an electric field, we get a magnetic field. Now, what this amounts to is, often enough, it gives us the following, that a moving charge will give us a magnetic field. And this is what we want to focus on. Of course, if you have a current, then there is a moving charge. And so what this gives us is that current I will give us a magnetic field. Right, so we go from changing electric field to moving charge, from moving charge to the current. We end up with that. Now, the right-hand rule that I'm going to teach you is used to determine the direction of the magnetic field B, given the direction of the current I. So you would literally use your right hand, take the thumb, point it in the direction of the conventional current, and I'm going to indicate that this is supposed to be conventional current. So not the actual one, not the electron current, but the conventional current. The thumb of your right hand, and it has to be right hand. This is the right hand rule. The thumb of your right hand points in the direction of the current. You curl your fingers around the wire, and the direction in which your fingers curl is the direction of the magnetic field. And then the magnetic field here is drawn. B is the magnetic field. So right hand rule. Use this to determine direction of magnetic field B. Okay. Now let's see if we can figure this out. We already did a straight wire, but we'll try it. We'll give it another shot. So if you have a here's a wire, and then you have charges that flow through it. Now we know that it's the electrons that flow, but right-hand rule works with a conventional current. So we're going to say that the positive charge flows with the wire here. So the direction of the current is that's the direction of the conventional current, the flow of positive charges. Electrons, of course, are the actual things that flow. They flow in the opposite direction, but we stick with the conventional current flow. Now, you would use your right-hand rule, so that what you would do is you would say that you would align your thumb, the thumb of your right hand, with the direction of the current. And so this is, your thumb would point like this, of your right hand. Then you would take your fingers and you would curl them. And your fingers would curl in this, let's see, yeah, they would curl in this direction. So I'm going to draw it, fingers would curl like this. And this would be the direction of the magnetic field. So I'm going to draw another one here. I'm going to draw another one here. I'm going to draw another one here. All right, and so now you have the direction of the magnetic field. B just curls around the wire in this fashion. If you move farther away, the magnetic field still curls. It's just a bigger circle. And then you could draw another one if you wanted to. And another one as you move farther and farther away. And I suppose you would put another one in here. So you have the magnetic field that curls around the wire. If you take this and then you loop it into a loop, you will get a slightly different field. Let's see if you can visualize that. So let's say you have a straight wire that goes like this, and then let's say that you have a loop here that loops around, and this thing comes back out. So this is what we have. Now let's say that the current flows this way, conventional current again. So the current I does this, flows all the way around, all the way around. This is the current I. It is the conventional current, the flow of positive charges, and then it comes back out this way. Here's your current I. Now let's use the right-hand rule to figure out the direction of the magnetic field at different locations. So how about we choose this point first here. So at this point, the current flows to the right, and you would align your thumb of the right hand with the current so that your thumb would point in this direction. Then you would curl your fingers of the right hand, and your fingers would curl like this. And that would be the direction of the magnetic field. If you're somewhere here, your fingers would curl like this. If you're out here, that's going to be tricky to draw, but if you're out here, your fingers would curl like this. If you're here, your fingers would curl like this. And then if you're here, your fingers would curl like this. And then here, they would curl like this. And somewhere here, eventually, let's see, you would your fingers would curl like this. Here, they would curl. All right, this one is a little, I think, confusing, but how about this one? Let me try this one. So this one curls like that. Goes under, and then this one here curls like this. So these would be the directions of the magnetic field. Now, I'm going to add something to it. Now, of course, let's forget this piece here. So, between these loops, you have more loops of the magnetic field. I only drew a few select ones. Now, if you move away from the wire even closer towards the center, you will have the magnetic field that points, well, it just points, it does the same thing. You just have a bigger loop, and then you 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 have a bigger loop. And so you could indicate that the magnetic field of this thing just sort of from here points like that out into the space here, and then here it points like this out into the space here, so it's back from there, and then it goes like this, and then somewhere here it goes like that and comes out. And so in that sense, you could say that here's the North Pole, and then somewhere down here is the South Pole. If I were to draw it in, if I were to look at it a little differently, let's say like this, so that here's loop itself. I'm looking at current flows in, goes, and then it loops around, comes back, and comes back out. But I'm looking at it from the side. What I would then see is that the magnetic field points like this. Right, and I could say that this is the North and then this is the South Pole. You could also do one more thing with this. That is, you could look at it this way, if it helps. Drawing the same field, but from different angles. So suppose you were to look at the loop from the top. So this is the picture you're looking at. Here's your loop. Right, the current I flows in, and then the current I flows back out of it. So then you could indicate the direction of the magnetic field with a certain convention, so that here the magnetic field is coming at you. So in this case, it's coming at you, so I can draw it like this. At this point, the magnetic field points out of the page. Here it points out of the page. Here it points out of the page, 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 points out of the page. And here the magnetic field points into the page. So I'm going to draw X's like this. So the convention is that X indicates into the page. And then that with a circle indicates out of the page. Out of page. We will need this convention. We will need these signs again and again and again. So this is the magnetic field here is doing this out of the page, and then in here, out of the page, here, out of here, out of the page, and then in here, and so on. Well, if it makes sense, great, and if it's confusing, I suppose it might be confusing. Now let's see what we get if we try to combine, if we take this loop now and we try to draw a magnetic field of a solenoid, so that what we have is the field, the current comes in, and then it loops around. So it loops around like this into a loop, but instead of coming out, it continues to loop around and it climbs upwards. Something like this, and then somewhere up here on the top, it comes back out. The current flows in, flows all the way around, keeps going, keeps going, keeps going, keeps going, and then eventually it comes out from the top here. So there's a certain height elevation between this point and this point. There's some h here, some height. Well, you would then have, what you would have is that the magnetic field produced by the first loop, which on the inside would point up and on the outside would point down. So the magnetic field of the first loop would combine with the magnetic field of the second loop, would combine with the magnetic field of the third loop, and so on and so forth. And as a result of that, on the inside, you would get a magnetic field that keeps, you might get a bit of a squiggly line like that, and it comes out. And then somewhere here on this side, you would get something similar, maybe a bit of a squiggly line, and it comes out like that. And somewhere here towards the edge, you would get also squiggly line comes out like that. Here towards the edge, squiggly line comes out like that. So all of these individual fields, see this field here will combine with the field above it, will combine with the field above it, and they would form these lines like that, and then they would loop around. Come back down, and so would this one, so would this one, so would this one. This would loop around, come back down. And you would have a direction of the magnetic field at points like this. I suppose I'll try to draw that one as well. So it goes like that. I'm going to draw this one also. So it goes like this and comes back. So this would be the direction of the magnetic field. Now, so let's redraw it. So what we would have is, and this is a solenoid, by the way. So this is a solenoid. Here's the first loop and here's the second loop. Actually, I have a better idea. Let's do it like this. So, one second. So suppose that I have this solenoid now. I'm going to draw it like this. Here's a solenoid that has a bunch of turns. Right, so here's this one, has a bunch of turns. There. And the current flows into the bottom. Loops around, loops around, loops around, and comes back out through the top. So here's current I. And going in. Then you would have the magnetic field that points like this. Just points straight through. And you would have the North Pole and you would have the South Pole. These two are equivalent. Perhaps this makes sense. Now these would loop around, come back down. And so with this one, this would loop around, come back down. And this one in the middle will actually have to loop around as well. All of these have full complete loops. But anyway, so we have that. Now, so here are the pictures of magnetic fields as depicted by ion filings. Here in this case, on the left-hand side, you have an actual magnet, and then on top of this magnet, you sprinkle ion filings, like literally small bits of ion, and then they will align themselves with the lines of the magnetic field. And so you would get what you would get. And so the magnetic field in this case for a magnet would just look like, well, it would look like this. It would be lines of the magnetic field, and then you come back, have a few more, maybe I'll add one more here, and then so on and so forth. Right, now in this case here, we have a single wire. The wire, here's your wire, and the current flows, you couldn't tell from the picture which way the current flows, but let's say that the current flows like this, so this is I. Then you'd have the magnetic field line that just loops around. So here's the magnetic field. Let me indicate that this is a magnetic field. And in this case, this is your solenoid. So you have a wire that loops around, loops around, loops around, loops around. It's one wire, one continuous wire. And then the filings will show you the direction of the magnetic field. If I were to draw it, I would draw something like this. That thing loops around, and the current comes in, and then the current comes out. So here's I, and then here's I, and you would have the magnetic field that points through, and it also points around. So here's your magnetic field. note that this magnetic field here is very similar to this one. So they look, perhaps they're not identical, but they look very much like each other. All right, so you have the right-hand rule. And here's the picture for the right-hand rule. You have to use the right hand, not the left hand. The thumb points in the direction of the current, and the fingers indicate the direction of the magnetic field. You would start with a single wire and gain the picture of the magnetic field using right-hand rule, and then from the single wire you move into a curved loop. All of this here is just the same curved loop. And then once you have a curved loop, you could take this loop and coil it into a solenoid, and this is a solenoid, and you end up with this magnetic field. Now you should understand the shapes of the magnetic field for a single wire, straight wire, for a loop, and for a solenoid.